who will tell us about shock formation for the Einstein-Euler system.
Thank you very much, Jan, for the introduction, and of course, thank you to the organizers for the invitation to be here. It's wonderful, of course, to be in Edinburgh, and also sort of in the post-pandemic world. I have not been to so many conferences, so it's great to see new and old faces. So today I'm going to talk about shock formation. Of course, we have already seen shock formation in this conference, in this beautiful talk of Jared. But since this is a conference on general relativity and dispersive equations, I feel that I should add Einstein to this. So the main result I'm going to talk about, it's joint work with John Anderson, who is sitting here to keep me honest. Okay, so let's start with the talk. So I'm going to talk about Einstein-Euler. And in fact, for the purpose of this talk, I'm going to look at just the case where the Euler is irrotational. Okay? So this is irrotational. There's a sense that one believes the irrotationality is not really fundamental. I'll tell you why sort of I believe that more than just mere optimism, but that will be halfway. Okay. So in the rotational irrotational setting, what's our equation? So the Einstein's equation is usual Einstein's equation. So the unknown here, it's a manifold, and I have my metric G, and then because it's irrotational, the fluid field is just given by a scalar field. Okay. So I want to look for solutions to the Einstein-Euler equation. So this is the Einstein part. And the right-hand side, I have the stress energy momentum tensor corresponding to my phi. And it's given by this. So this is a function L, which let's just call it a reasonable function. And doesn't really matter what it is. And it's this plus L sigma of G mu nu, where sigma is simply minus of G of phi d phi. Okay, so that's my T, and my phi satisfies just wave equation. Okay, so the Euler equation is just a wave equation for the scalar field. So D is the Lagrange connection for metric G, and I have the equation that looks like D of again this reasonable function L, which I'm not going to say anything else about, of this phi equals 0. Okay? And sigma is again that sigma. Okay? So it depends on phi quadratic. So I want to study this, and I want to study shock formation. So here's the main theorem. As I said, it's joined with John Anderson. The writing is not complete yet, so yeah, be careful. So the statement is the following. The statement is there are solutions which form shock. In fact, there are a lot of them. They are stable. Okay, so let me just state it as follows. So there exist shock forming solutions. So let's call them G naught and phi naught. So these are fixed solutions that form shock to this system star, right? For appropriately chosen L. Actually, maybe there's one thing I should have to say before this. So one of the important thing about L and so on has to be chosen such that one important assumption I need for this is that I want to say the speed of sound it's smaller than the speed of light. Okay, so if you look at the Euler part of the problem, it has its light cone. Right? So this is the second wave equation. So this light cone for Euler has to be inside the light cone for Einstein. So speed of light is faster. Okay. So now for reasonable choice of L, and assuming this, there would be shock forming solutions to star, which are stable, And let's sort of maybe roughly say what do I mean by these statements? So that is to say, for let's say order of epsilon perturbations of them of its data, the following holds. So first of all, for everything, if you perturb small enough, you will still form a shock. Okay, so the first thing is that there exists some shock forming time, right, which is like the shock forming time of the background. Let's call it T star naught plus a little bit small, right, such that the solution becomes singular at time T star. At time T star. So this is a singularity formation result. So we're at the singularity formation conference. And I can tell you sort of what the singularity looks like. I can tell you that the singularity looks like a shock. Okay. So what does this mean? So this means that at time T star, that's what I call it, the fluid variables blow up. So the fluid variables, since phi is a fluid potential, the fluid variables are actually derivative of phi. So well, no. So the derivative of fluid variables blow up. So what I want to say is phi remains C1. In fact, the kind of things we choose, so that it's still C1 alpha or some alpha positive, but the C2 non blows up. But the C2 non blows up. Non blows up. And in fact, the C2 non blows up exactly because of shock formation. And the C2 blow up is caused by shock formation. Blow up is caused by characteristic hypersurface touching each other. Characteristic. Hypersurfaces touching. Here's the picture. So you have a nice null hypersurfaces. They are all intrinsically quite nice, and then but then they at some time t, right, they touch each other. They're two differently touch each other. These are things which are not so easy to draw, but okay, morally you know what I'm saying. Okay, so that's the second thing. But now the third thing I want to tell you is at times T star, what's going on with G, right? Because I'm solving Einstein-Euler. So at time T star, G is actually still quite regular. At time T star, I want to say G is actually G remains C2O. Yes, for some alpha. That's there. Okay, so let's make some remarks about the result. So the first remark is that the shock formation, it's known if you look in symmetry. Okay? So shock formation is known in plane symmetry. And this is by the work of Randall and Stahl. I tried really hard to remember the date, but I couldn't. So I think it's 2008. 2008. So there is a sense that our result, I'm not going to say much more about sort of exactly what's the shock forming solution I'm talking about, what's the regime that I'll be thinking about. But one thing that should be said is sort of our regime is a perturbation of plane symmetry. Okay, but we can't really sort of perturb everything that Randall and Stahl are constructed, but we can find a subclass for which we can get a bit more information, and then we can perturb those, and those are stable. Okay, so in particular, the story starts with there's okay. Now, second remark. The second remark is from now on, I'm not going to think about the problem as a problem of Einstein-Euler. And I really want to think about the problem. We'll think about the problem more generally. The problem more generally concerning coupling a shock formation wave equation forming wave equation with non-shock forming wave equation. So there's a particular case that we are thinking about, which is a couple Euler with Einstein. So shock forming wave equation, and in this case is Euler with a different, let's say, hyperbolic equation. Hyperbolic equation, right? In this case, it's Einstein. So I want to, for the rest of the talk, think about this result just in the context of, suppose you have something that forms shock. I want to couple it with something else, and okay, what can I do with this now? Okay. So in particular, in our case, what we'll be thinking about is, of course, we roughly have that already Euler. Of course, I have already a wave equation here, right? So Euler already have a wave equation. So let me just write this. Euler has a wave equation. I want to think of this as Euler has a. Oops, sorry. Euler has a wave equation. Let's say with respect to a metric h. Okay, that depends on phi. This has to do with d and d phi, and I have terms that has to do with let's say dg d phi, something like that. I'm thinking something like this. This is my Euler part, and I also have an Einstein part, for which I choose a wave coordinate for Einstein. And after I choose wave coordinates, of course, the Einstein's equation becomes like a wave equation for G. So I want to think of it as something like box of now G of the components of G. Of course, the Einstein part itself is nonlinear, so I'm going to think about this as some nonlinear thing with dg squared. But of course, it's coupled to Euler. We will also see Euler. I'll be looking at the equation of this. Okay. So I want to think about this kind of question. Okay. So now here is the third remark. The third remark is the following. So suppose you want to think about sort of this coupled system, right? As I have just written down. Now you want to look at, let's say, the equation for G. Okay? So it's a wave equation. So I have box G of G is equal to, let's say, d phi squares. This is from the Euler, so that's how. So from the wave equation of G, right? So this equation. Now you tell yourself the following things, right? You say, okay, this is a wave equation. What does wave equation do? Wave equation, if you control the right hand side L2, you control the left hand side with one derivative L2. So I know I told you sort of I was measuring things not in L2. I'm measuring things in C, but let's forget about that. But what I'm telling you in the result, right, is that, well, if you just look at this, right? So if the left hand side is going to gain you one derivative, the right hand side one derivative phi, you would think if you can control one derivative phi, you will control one derivative G. But the result tells you that there's something that's slightly sort of surprising, which is G is actually slightly better than phi. Right? Forget about, we're thinking about C and L and different things, but this is one order of regularity better, right? One might only expect, maybe you don't. G to be only in C1 alpha, but things are actually better. And why is it better? But the better regularity comes from the problem being having two speeds. Comes from the two-speed nature of the problem. In particular, the important thing that I earlier forgotten to draw, right? So the Euler speed has to be smaller, right? This is very important to get Okay. So now here's the rest of the plan of the rest of the talk. So I'll talk about some related works, sort of what has been done. First about shock formations, but also about sort of what shock formation is known. If you know you have a shock formation, shock forming wave equation and couple with something else. And I'll talk about sort of known results, sort of slowly coupling with more and more complicated things. And then I'll tell you how to couple with Einstein. That will be the rest of the talk. Any questions up to this point? If not, let's start with what related work. So I want to have something that forms shock, and again, slowly coupling with more and more complicated things. So what's the simplest thing that I can couple with? Of course, that would be nothing. Right? So I'll just look at quasi-linear wave. Quasi-linear wave, and I want to understand shock formation. Okay? So that's the first thing I want to do. So let's look at the following model. So let's look at Fox H psi equals 0. Okay? So of course you complain it doesn't look quite like that, because this is a box of phi involving d phi. But I want to claim it sort of does if you think of psi is equal to derivative of phi. Then you will cover something. You just differentiate and you get wave equation. Okay, there are right hand sides, of course, there are things to think about, but let's. So this can already form shock. Of course, there's a long history of works about sort of shock forming things, for in particular this kind of thing in one dimension. But since Jared already mentioned a lot of that literature in his Tuesday talk, let me dive right into high dimension case. Yeah. So in high dimension case, the first sort of shock formation result was the result of Berliner. And it's a beautiful result from 1999. And what he showed is that he proved shock formation in the setting where when you have shock, when you look at the first time where you have shock, there's exactly 1 point on the first time that there's shock. So exactly when there's exactly 1 shock point. And you think this is a setting where the secretly sort of the shock surface is convex, so it's convex time. And if you want to measure things up to time first time, that is probably a picture that Jared also had in his talk, then you see that. So that's slightly easier to understand because there's only one enemy that you are dealing with. But from now on, I'll try to think about the other approach of shock formation by Christodoulou, which is 2007. So what he does is he introduced a fully geometric approach. In particular, with the fully geometric approach, let's say even in this case, when you have 1 point, you can go a little bit further than the T. You can get a little piece of the actual shock surface. Okay, and this allows him to actually later. This is important for shock continuation. Because if you can't even get to the shock surface, it's not so easy to go beyond the shock surface. So from now on, I'll think about everything in the fully geometric approach. Notice that our result doesn't really get the shock surface. We are just doing everything up to time t, but I want to think in a way that potentially allows you to go beyond. Okay. So what did Christodoulou do? So the way that he thought about this problem is he actually tried to introduce a new coordinate system to think about. To introduce a new coordinate system. Since this is intense, let me get it. Okay. So, well, what you do is you start with, you originally have some coordinates given you in the problem, let's say x, y, z. But now you want to look at a new coordinate system where you change one of the coordinate. Instead of x, you use u. And what's the special thing about the u? Well, the u is something that that exactly would see the null hypersurfaces, because of course the null hypersurfaces are the main player of shock formation. So you would look at these are from shocks, so these are hypersurfaces. But okay, that's the best I can draw. So these are u equals constant hypersurfaces, right? And if you want a formula, right, what this is if you look at this quasi-linear wave equation, you want to solve for this being null. So you solve for h inverse of du in 0. Okay? So you want to look for hypersurfaces that look like that. And the idea is to try to prove that the solution is regular. With respect to these coordinates, with respect to differentiable structure given by u, y, z, you want to say everything is regular. But okay, so then okay, if you prove everything regular, where's the blow up? Well, the blow up comes from the fact that this map, you can't go back. It's not inverted. Okay, so what he did is he introduced mu inverse correlation density, which is minus 1 over g of du dt. Okay, so you have this u, which is null hypersurface. You want to understand sort of how it interacts with constant t, and you want to say something is shrinking going to 0, and that's a shock. Okay? And you want to say try to prove first of all that the solution is regular, and second, you want to show that this thing that's defined by this will actually go to 0 in finite time. So we want to say that combining this will give you a singularity. Why? Let me come here. So what you then want to say is you want to understand sort of the transformation between these two things. Okay? So as to not be so confusing to have sort of different partials in different coordinate system, let me introduce a frame. So corresponding to the coordinate system, P, U, Y, Z, introduce a frame that's regular with respect to this differentiable structure. The frame is L, I will call X graph Y, Z. Okay? So it will be what you think it is, modulo, okay, something that I will not even try to explain. So you should think that L is sort of like d by dt in this coordinate, prefix is like d by du, etc. So in particular, if you again look at this picture, L is tangential, X graph is like that, and Y and Z is sort of in the direction you cannot see, right? Going into the. So now what's the transformation? Well, what you want to say, the transformation looks like the following. If you just give me a partial with respect to the original coordinate system Tx, Y, Z there, then if you write it in terms of this, you would get something like L and Y and Z, but the singular in terms of the d by du, the X graph. Okay? So it's singular like that. So in particular, if sort of everything is regular with respect to this, and if mu goes to 0, as you would try to prove, then the usual derivative actually would. Okay. So right, so right, okay. So that's that. So now so indeed this can be achieved. And now the next thing I want to say is that this can be achieved. And oh, sorry, I want to also say one more thing. Okay, this can be achieved. And moreover, what does the singularity look like? And the singularity looks like looks as follow. And moreover, we know that in fact mu will go to 0. Of course, it has to go to 0 at time t star when there's a singularity. Right, this way 0 is singular. And if you look at mu, let's call it mu star, which is the minimum of mu over the spatial variables. Let's say, I want to say this actually would, when you are near the singular time, this is linear. So you go to 0 linearly and you have a blow up. And one way to see the linear blow up is in fact the following. Is in fact you can say that L mu, okay. So along so fix for any fix u y z, right, in this coordinate system, you look at this is roughly a constant. So it's roughly a constant. So it's really pushed. This is a derivative. It's pushed to 0 linearly. So therefore, it looks like that. But now, if you are a bit more careful and you want to look at the finer structure of what the shock look like. So in fact, if you assume, if we put in non-degeneracy assumption, whatever that means, I can say that, of course, along every null curve, right? So this is just constant. So I'm just pushing down. But I'm just wanting to say what there's a particular value of u where you push down particularly fast. So there's a shock, and away from the shock, things become slightly better. Okay. So in formula, what you can capture is that you can say that in fact you want to say that mu of t u y z, right? I told you that if you take the minimum, it would roughly looks like t star minus t. But if you have a non-degeneracy condition, actually you can say that, well, everything only, let's say, becomes 0 at, let's say, call it u equals 0. So it actually looks a little bit like that. Yeah. So this is sort of the precise description from what Christodoulou has of the shock formation. Okay. So let me maybe say one thing. This all looks so good. Of course, you also remember the book is 1,000 pages, right? And the difficulty is actually, it's okay, this sounds so good, I mean, on the board, but in practice, to try to do this is difficult. And in fact, you cannot do this. There's some difficulty in the top order because it seems like you want to lose derivatives. So in order to save it, use a geometric idea associated to Ratchaduri, but that actually costs you in mu weights. So that's a complicated story. So you can't really do that, but you can almost do that. And you can really do this for low level derivatives. If you close everything into 20 derivatives for the first 10 derivatives, is indeed true. Okay, so that's the caveat. All right, so now let's start coupling. So the first thing I want to couple is I want to couple quasi-linear waves. That's transport. So that would be the simplest. If I want to understand this thing, would be shock forming. Of course, I'll still look at this shock forming. I want to couple with another hyperbolic thing. Well, the easiest hyperbolic thing I can imagine would be just a transport equation. Okay, so let's couple that and see what happens. So here's a model. So remember, I have this psi, right? It used to be this equals 0, but let's say now it's coupled with something else. So let's say it's coupled with psi times f. Okay. And f satisfies the transport equation. And let's say the transport equation looks like dt plus some function b of psi of the gradient of x of f. And let's say this is equal to f times partial psi. Okay. So of course you ask sort of who cares about this model? And this actually was studied because the Euler equation, if you forget about well, if you add in vorticity, if you don't stay in the irrotational regime where you have a wave equation, actually looks like this. Okay. So this was studied in slightly different language, but in my joint work with Jared Speck in 2018. And let's say this is a model for the Euler equation, still, let's say, isentropic Euler equation, but without irrotationality assumptions. So in that setting, you should think that psi is fluid variable. Let me say here. So psi, you should think, is fluid variable. Velocity, density, etc. And what is F? F is equals to the derivative of vorticity. Vorticity. So the equation looks like this. This is really looks like this. So now let's try to couple, right? I want to say, okay, look at this. I want to say whatever Christodoulou has in this, right, this kind of shock formation picture would be stable even though I add F2. Okay? So that's what I want to establish. So let's try. So let's recall what we have, right? So we recall that we have, right? So from the Christodoulou picture, right? We know that, of course, psi is bounded. Right? These are regular. But on the right-hand side of, let's say, the transport equation, I have derivative of psi. Okay? And remember, derivatives are bad because derivative, if you translate to regular things, there's a mu to the -1. So therefore, if you just look at derivative of psi, this is order of mu to -1. Okay. So this already looks quite bad because right now you look at this equation. You know the derivative of f is something that looks like one over mu times f, right? So this, so you think you would like, so this would lead you to think you would have dt of f, right, equals to f mu to -1. Okay. I told you how to think about mu to -1. Mu to -1 looks like t minus t, right? So if I roam all this, integrate this up, this I cannot integrate because I get a log, and okay, this constant is okay, just 1. So therefore, I get if I just do it like this, I get that f. I only get a bound that says, well, it's like mu to the minus the constant, right? But of course, mu is going to 0, so near the singularity. So this is certainly large. So it seems not perturbative. Seems not perturbative. Okay. That sounds like bad news, but in truth, it's worse. So why? So because of course you cannot close the problem by just looking at f, right? These are higher dimensional problems. You have to commute with derivative. Okay? So it's worse when commuting with derivative. So what's the issue here? So let's think. So of course, in the transport equation on the right-hand side, I have something that's derivative of c. And derivative of c, right? The regularity that I have, it's only with respect to the geometric things. Right? It's only with respect to these guys that c is regular. So if I'm to differentiate this equation, I better be differentiate using these vector fields. Okay. But of course I can't. Let's say if I want to differentiate this by L, I notice that I have to commute this in, right? I have to commute this with partial. But partial looks like mu to -1. So when I commute in, I'll hit mu to -1. So this commutator is bad. So I'm saying that this plus this, right? This looks like what? This looks like O of mu to the -1, breadth x plus O of 1, L plus y plus n. Okay. So I can't commute this. Okay. So now what do I do? Well, of course, I noticed that the only issue is this. So let's multiply everything by mu. So if I look at mu of this, so I have this f. Now things look much better because I have O of 1 of x f(x) plus something that's more. And this is L plus y plus z. And all of this hitting on f. And this is equal to the right-hand side, right? Which is equal to, if I multiply by mu, this is also becomes regularized. So this is like something nice. Let's say regular. Okay. So this is because this is 1 over mu. I multiply with this regular. Okay. So now it's better. I can commute in. Okay. And now here's the problem. If I hit an L, if I have an L here, right? I want to commute in. But it commutes with all the other vector fields, right? Because that's consistent with the differential structure. That L is going to hit mu. If I commute 10 times, this is going to hit 10 times, and my product rule actually it comes with a factor of 10. Right? So when I commute, what I get is that when L hits on here, I would get a term. So when commuting, so commute. So after commutation, what do I get? I get the mu of this. Let's say if I take 10 derivative, L10 of f, this would be equal to the worst term is when I have one thing hitting on here, right? So I would have L mu, and then I would have, let's say, let's not write everything. I don't have a lot of time. The other 9 will hit on here, so I have a term like this. Okay, so this I have this. I can of course divide the mu. Why is this worse? Well, this looks like what I had before, right? This looks like what I had before. I have dt of something equals to 1 over mu of something. Okay? But of course, I told you the constant is large. The constant is like 10 here. So the more I commute, the constant becomes worse. And the constant that I get here also becomes worse. Okay? So there's no sort of conceivable design scheme you can do to say that top order you do something and you come down because the constant becomes worse. Okay. But finally, how was this problem solved? Because of course, all the problems that I was showing you was fake. So the point is the following. So the point is that dt is transversal. Well, and this is sort of the two-speed nature of things I was talking about in the very beginning, where Einstein-Euler you gain some regularity. It's because this in the real problem, in the Euler problem, these two derivatives they're different. And remember mu looks like what? It looks like this star minus t plus u squared. Right? So things are really only very, very bad when u equals constant, but this is transversal to u equals constant. What does that mean in practice? In practice, what this means is that this O of 1 that I say here is actually non-zero. Right? So this is non-zero. And because this is non-zero, now you can imagine multiply f to this. This is d by du. You can integrate by parts, and you can do an energy estimate on constant u hypersurface. Right? So this leads to the possibility of doing energy estimates on constant u hypersurfaces. Okay. So why is this good? So now, what you have is that you have an error term. So the main error term looks like coming from this guy, right? Looks like L to the 10. So if you do energy estimate, square F mu d volume. Okay. And what's the volume form? This volume form in coordinates actually looks like this. D, let's say the two-dimensional is sigma, d would be, so there's a mu in the volume form. So this is still okay. If you do energy estimate, you still lose because there's a mu in the volume form, but there's a mu in the volume form on the left. If you do ground wall, you still lose. But now the point is that you get a good term, which is on constant U hypersurface. And what's a good term on constant U hypersurface? This is this, and this is d sigma. Instead this is constant U. I just integrate. So I have a bulk term, and on every constant U, I have the term. This has a huge constant, right? Let's say 10. That would be very, very dangerous if I ground wall in T, because things are bad in T. Right? I have this blow up rate, but there's no problem ground walling in U. Ground wall in U and that. Ground wall in U and then that. In fact, sort of a variation of this idea, you can also do even in the 3D case, right? Where, of course, the problem is not just simply a transport equation. There are things which looks like they will lose derivative, but fortunately, they are elliptic structure that allows you to gain something. And the elliptic things, it's coupled with good nonlinear structure and also good transversality properties. And actually, all these ideas work also in 3D. Right? So that's also work with Jared. More recently, 2021. Okay. So far so good. So now I want to get to sort of what I want to talk about, right? So I start with quasi-linear wave, now I couple with transport, but really what I want to do is I want to do quasi-linear wave coupled with quasi-linear wave. So while I'm erasing the board, let me remind you, you all remember on Tuesday, right? Jared has a slide with a lot of sort of previous works on shock formation, etc. It was a rather comprehensive list, but he forgot one very important work, which is his own. So this is quasi-linear wave plus quasi-linear wave. So this is what Jared did. Let's try to. So this is the work of SPAC, as I just said. Again, 2018. Okay. So now I want to couple quasi-linear wave with quasi-linear wave. Okay, so let's do that. So I have something like I think not split it up on the model I want to think about. So it's slightly different because wave is different. So I want to think about this one. And now I have a different box of G F of F, and then I have something like F d psi and psi d. Okay. So what did Jared do? So Jared do this problem actually in the opposite case of what we were interested in. So he did the case where if you look at the two cones, okay, so remember I wanted the shock forming thing, which is psi, to be slower, to be the inside cone. Jared actually did the case which is the opposite. Okay? So if you look at this, so this is the cone for H, and this is the cone for F. So as you already see from the
yeah. In your result, you get existence up to where? Where do you stop?
So constant time, the first singular time. Yeah. And then of course what Jared and Leo did, as you heard earlier, is even with transport, with vorticity, all that, right? So you can go. We did up to we did up to first time. What they did is that they get the whole.
No, I'm talking about the new result.
The new result is also single with John. You mean constant time. Constant. Yeah. So okay. So yeah. So that's the problem that Jared solved. Okay. So of course this already I claim.
Sorry, would you not expect that if the singularity you expect in gravity is so weak, you should be able to go up to that one?
Sorry.
In your setting, the new one, right?
Yeah.
If the singularity, the gravitational singularity you
Uh-huh.
will get will be so weak, right?
Yeah.
Then you should be able to go up to it and even past, which you wouldn't expect it.
So, so you want to talk about the result? So I would think that right. So I would think you would be able to certainly get the crease.
Yeah.
You will be able to get a little bit beyond, and you will get the Cauchy horizons. But now the Cauchy horizons is determined by the gravity,
By the gravity.
Yeah. because that's fast. And you'll have a weak singularity.
So a very weak.
This I'm not so sure, because if you look at okay, I don't know.
You
So
said
this could be very, very weak.
C2
This could be much
alpha.
weaker than what's happening.
Okay, so you said C2 alpha, but that is way weaker than what you've done with Igor.
Exactly. Yeah.
So then you would expect you can handle it, then
You
maybe.
can handle, I would expect you can handle everything up to this no cones of law. But of course, here there's some blow up of the gravity too. So the C3 will go up. Yeah, I didn't say that, but yeah. Okay. So come back to Jared. So right, okay. So now let's see how to do this problem. Of course, right. Of course, even in the model in the transport, we have seen that it's incredibly important to actually have the transversality of speeds, right? Because if you just integrate along sort of 1 over t star minus t, right, there's no way to gain it. You really need to use that. Okay, you are integrating not along the integral curves of L, so as to gain. So this gives you a good chance, right? Because they have different speed, and in fact, sort of morally, the same type of ideas work. And there's sort of two main things here. The first main thing is that, well, you can still now do energy estimate. What's the main thing to capture transversality here? The main thing is so that you can do energy estimate on constant U hypersurfaces. Okay? So this also works because constant U hypersurfaces is of course characteristic for psi, but that's faster. So those are space-like for F, and okay, you can do energy estimates on space-like hypersurface. There's no issue. Okay? So this is you do energy estimates on constant U. Okay. This is okay because space-like from the point of view space-like for F, or maybe for G, for magic G. So that's half of the story, but there's another half of the story. The other half of the story is how do you compute? Because in transport equation, it's incredibly important that I was a first order operator. First order operator, if I multiply by mu, it's already regular because of how things behave. So then if I multiply by mu, I can compute, that's good. But box is worse, right? Box is a second order operator. Even if you multiply by mu, you commute because this doesn't really see the structure of that box. So that commutative will be bad. In fact, you would think you would have to multiply by mu cube. That would be pretty bad for the estimates. Well, however, of course, we all know that we can think of box as if it's first order. Right? You can think of this as so we write box as the first order symmetric polar system. We can always do that for commutation. Okay, and that sort of is the other piece of the puzzle, and then you can have this. Okay, so now let's go to our problem. So I guess now I transition to ideas of the truth. But this is the part 4, if you continue that. So this is quasi-linear wave plus quasi-linear wave. I can look at essentially the same model, right? Same model. I claim you can get this model from what I wrote earlier for Einstein-Euler after derivative. If you identify psi to be derivative of phi, and f to be derivative of g, then you would get something that looks like this. So I guess that's not quite good. But almost. Okay. So you have similar, okay, but now the opposite speeds, right? So the opposite speeds, but with opposites. Opposite speeds. Okay, fine. So let's try to deal with this. So what do I do first? So first I sort of learned what I learned from Jared. I first rewrite the box F. Let's say in this case is symmetric. I want to write it as first order symmetric. Okay. So we write as first order symmetric hyperbolic system. So the first thing I do is first order symmetric hyperbolic system. So what do? What I first want to say is, well, I still have my psi, so that doesn't change. So that I don't confuse myself, let me call okay, let's that was not prepared. Sorry. So I revised specialized hyperbolic system. So let me actually look at G to be equal to partial F, which is roughly you should think as second derivative of G, right? According to this identification. Okay. So now I have so what do I get? I have a first order operator. Let me just call it D. Okay. Maybe the script D. Okay. So I would have D of G is now equal to something that looks like, for instance, let's just look at the main term so that's a second derivative, so that's something that looks like this. Plus. Okay. So there are two things I know. The first thing I know is that all the commutations I should do with respect to the regular vector fields. But the second thing I know is that my main enemy is actually the commutator. Right? I told you that somehow in previous case, the main enemy is when I commute, and when I commute, I get something with a large constant, which I have to integrate with the log. And now I cannot really do energy estimates on the now time-like hypersurface. That seems to be a problem. Right? So let's maybe say it like this. So the main enemy is the following. So instead, I want to control, so at the energy estimates, I would have something after commutation. I would get something that controls LG squared mu d sigma du, right? And I will bound this by data plus a term that's look like so I have integral and then I have d sigma du dt, and let's put the mu here, and I have LG squared over mu. Okay, so that would be the volumetric term. Remember this constant is 1. Okay, so if I grow more, I would get something that grows with it. That's up. Okay. So how do I deal with this? So there's sort of two ideas that one can try to use to deal with this. So the first thing one can try is, well, why not still try to get energy estimates on constant U. On constant U. So of course you say, well, this is crazy. This is time-like. How can you get energy estimate? But okay, let's forget about that and just do it. Okay. So what do you get? What you get is you will get a term that you would like, right? You like this term, LG. And now you have a good weight in mu. So this is on constant U, right? So this integrate. That's a good term. Okay, that's good. In fact, you have more than one good term. You have a super good term, right? This is even you have this. But of course, there's no way that you can make the energy positive. It's time-like, right? So then you have to pay, and you have to pay this. Right? So there's no way around. That's what's going to happen. Right? So you have two terms which are of a bad sign. This is du, d sigma dt. Okay. So that's the first thing that doesn't work. Now, what's the second thing? Second idea you can try. Well, the second idea is the following, right? You say, well, actually, all the problem is coming from I'm commuting with L, and I have a constant one. What is this constant one? This constant one is finally L mu, right? I remember L mu is the thing that pushed me to the singularity. L mu is like 1. So the problem is if I commute with L hits on mu, and okay, this will be order 1 growth. How about I try to not commute with L? So what about I try to commute only with Y and Z? And of course, you tell me that's not possible because Y and Z and L and all these are constructed with respect to the different metric. This is a different, right? This is a different metric. Yet there's no reason there's no geometric reason that you can only commute with this and not see terms that you have to control with the other commutators, right? So what that means is that you will have error term, right? You can try to control this, d sigma. So what do you have? You will have things that looks like, well, you will have terms that looks like y mu over mu yg squared plus y mu over mu lg squared. So the first term is actually harmless, but at least you can consider regime for which, because L is the thing that pushes the singularity, that has to be size 1, y can be small. Okay, so if this is small, it's a small constant over t minus t. You integrate, you lose a small power. Okay, this we can handle, but this looks dangerous, right? If you have this, and in particular, this also has L, and in order to close this, it seems that you have to also commute with L, and commute with L have this problem that I was telling you about here. Commute with L have this problem. Okay. So what's the final resolution? The final resolution is, fortunately, it's not. We don't have one idea that doesn't work. We have 2 ideas that don't work. So we put them together. So the idea is the following. So what I want to do is I want to use this energy estimate. Of course, on constant U, that's too weak, but I want to use 1. So use 1, but averaged in U inside some small interval. Okay. And when I do that, what do I have? So let's go here. So I have an extra term, right? So I have extra term of these things, right? So I have, so let's now completely make the board crazy. So what I will have is I will have terms that looks like this, right? But moreover, integrate du from minus delta to delta, right? For the average, so I gain a constant, and all these belong to the left-hand side. But now that's good because this constant is large, and I can certainly use this to control this term, right? Whatever large constant it is, I choose delta inverse to be larger in a small neighborhood of u equals 0. But remember, away from u equals 0, mu is better, and there I can just integrate. Okay. So I can almost have everything except, okay, this it's not really coercive, so I have to pay this error term. Okay. But now I see that if I try to control this error term, right, with this, it of course couples back in what I have to control here. But when it couples back, I gain a small constant. Because I told you L mu has to be large because everything is pushing to the singularity. There are regimes for which our y mu is small, and you can construct this so as to have this small. So then putting these together, you can close the estimates. And now sort of the general idea is clear. So you construct sort of a hierarchy of norms, right? And such that you have to put some smallness constant in the YZ commutations, right? So as to say every Y Z commutation, the thing becomes much better, right? So that's your norm. Okay, that has an extra, whatever you call it, epsilon in it, and you want the epsilon to be much bigger than the delta, and you want the delta inverse to be much bigger than the constant you have to beat, and you put everything together. Okay, sorry. Actually, I have 1 minute left. Okay, so let me just end here. Thank you very much.